This is lesson 2.3, velocity and acceleration. I apologize in advance for my voice. I seem to be losing it, so hopefully it will last throughout the whole video. I thought this would be a good time to take a break from learning new derivative rules and look at a practical application of derivatives. For those of you that have taken physics, you'll be familiar with a position time graph or a DT graph. They're graphs that have the time along the x-axis and the change in position along the y-axis. And these typically will look something like this. So I have my time along the x-axis and my displacement or my position along the y-axis, and they just simply graph a change in position over a given amount of time, and they can look lots of different ways. The DT graph can be used to figure out the velocity over a given time, and this is done by taking the slope of the DT graph over any given period of time. So if we were to look at this particular graph, and I wanted to know the instantaneous rate of change or velocity right at that point, I could take the slope of that graph by using my slope triangle and simply knowing that slope is equal to rise over run, and I'd be able to calculate that. If we think about what the rise over the run is, time is in seconds and our position is usually in meters. So our rise is in meters and our run is in seconds, and that would give us our velocity in meters per second. This same slope principle can be used to find the acceleration by taking the slope from a velocity time graph. You may have seen this chart before. So if I have a DT graph, so a position time graph, if I have a velocity time graph, or if I have an acceleration time graph, I can go between the three of them. If I take the slope of a position time graph, that will give me the velocity time graph. And if I take the slope of a velocity time graph, that will actually give me the acceleration time graph. You may have seen it before. If not, this is a usual piece of information to add to your rules to live by. I would add this to your rules to live by. Now, most of the motion you would have analyzed in physics used a graph that would have been uniform, meaning that the DT graph would usually be a straight line or a composite shape made up of other straight lines. So you might be used to seeing something that maybe looks a bit more like this. So here's my displacement, here's my time, and you might be used to seeing something like that, moving away from home at a set rate of, at a set pace, or with a set slope. In the real world, motion very rarely happens perfectly, which means our position time graphs end up looking more like curves than linear functions. So more like this one than like this one. Can you see where I'm going with this? Calculus allows us to find the rate of change along any curve at any instant in time. So along any curve, so anywhere along here, it allows me to find that rate of change at any given time, that IROC, that instantaneous rate of change. It doesn't matter what the shape of the curve is, so long as we know the equation for the curve or the function, we can determine the equation of the tangent line for any given value of x, which really is just finding the slope. So let's say if my distance time graph is represented by an equation, so let's say S of t, so that's position at any given time t. So let's say it's represented by 3t squared plus 4t plus 1. And I want to determine the equation that I could use to calculate the velocity. I'm just going to take the derivative. And we know how to do that already. We've already learned how to do that. So for this particular function, my velocity time will be equal to the derivative of my position time. And I can find that So if I have using my power rule and my sum and difference rule and my constant rule, so my derivative of 3t squared plus 4t plus 1, 3t squared is the power rule. I'm going to take the power and bring it down. 3 times 2 is 6. My t stays, and 2 minus 1 is 1, so that just becomes, so 3t squared becomes 6t. Now I'm going to add my derivative of 4t, which is just 4, and my derivative of 1 is just equal to 0, so I'm not going to include it. So my derivative is equal to 6t plus 4, which means that my function for my velocity is 6t plus 4. Let's look at a graphing example, and then we'll get into some more numerical examples. So given the displacement time graph below, let's graph a velocity time graph and an acceleration time graph. We're going to use what we know off of this particular graph to determine the equation. So what do we know? Well, we know the zeros. We can see where it crosses the x-axis is at 0, 0 and at 2, 0. So we know our zeros. So our zeros are at 0, 0 and 2, 0. We also know our vertex. We can read that off of the graph, and the vertex is right here. We have a vertex in this case of 1, 2. Now we can use those zeros and the vertex to get the equation for the parabola. And we'll find this by putting those values into the vertex form of the equation and then finding our a value to fill in that missing piece. So we know that y is going to be equal to some value a times t minus 1 squared plus 2. So this is my h value and this is my k value from my vertex. There's my h, there's my k value. And I just filled those in. So now I'm going to set this to 0 to figure out what my a value is. And I'm going to fill in one of my points. So in this case, I'm just going to use when x is equal to 0. So 0 minus 1 squared plus 2. 0 equals a plus 2. So my a value is going to be equal to negative 2. Now I have all the information that I need to put this into an equation and create this equation. So my equation ends up being y is equal to negative 2 times t minus 1 squared plus 2. This negative 2 makes sense because it's opening downward. The plus 2 makes sense because it's shifted up. So now we're going to expand this out and simplify it. So when we expand it out, because we want to get it into standard form so that we can take the derivative of it. So we end up with negative 2, and that's t minus 1, that's just t minus 1 squared plus 2. That's going to equal negative 2t squared plus 4t minus 2 plus 2. My minus 2 and plus 2 cancel out. So I'm left with an equation for my position time graph, or S of t, is equal to negative 2t squared plus 4t. So now that we know that, the question is now asking us, well, what's my equation for my velocity time? Well, my equation for my velocity time is simply just the derivative of my position time. So I'm going to bring the 2 down and multiply it by negative 2, so I get negative 4t, and then 4t, the derivative of that is just 4. So now let's graph this on the velocity time graph. So what does this mean? Well, this is telling me that for this particular straight line, I have a y-intercept at 4, and my slope is negative 4. So we can go ahead and we can graph this on here. So I know I'm going to start at my point. So my intercept is at 0 and 4. And I know it's going to go down 4 and over 1. So 1, 2, 3, 4. and over 1, and let's put one more point, 2, 3, 4, and over 1. So there is my not so straight line for my velocity at any given time is equal to negative 4t plus 4. So that's the graph of my velocity time. Now let's do the same thing for the acceleration. Acceleration is just the slope of the velocity time graph. So in order to turn this into a acceleration time equation, I am going to take the derivative of this one. So my derivative, I have negative 4t, so my derivative of negative 4t plus 4 is just negative 4. And so that means that if I were to draw this on the graph, that my acceleration is right here at negative 4. So that is at equals negative 4. So let's lay down some rules, or let's just write down what we've just seen. So for any object moving in a straight line with a position function of s of t, and this is just our position function. So whatever that equation happened to be that was represented by our position time graph, I can find the velocity function by taking the first derivative of that position function. So the velocity function will be equal to the derivative of the position function. If I want to know what the acceleration function is going to be, or a at t, then I can take the derivative of the velocity function, or I can take the second derivative of my position function. And that's what this is saying here. This is my second derivative. So when I take the derivative of a derivative, I get the second derivative. We're going to talk more about second derivatives later in the unit, so I don't want you to get too hung up on it right now, but that's what we've got going on. And I've included it on here in Leibniz notation for those of you that might want to see what that looks like. Like I said before, I don't use it a lot. I tend to just use regular notation, but there it is just to see. So let's look at an example. So the position of a particle moving along a line is given by the equation s equals 2t cubed minus 21t squared plus 60t, where t is measured in seconds and s, the position, is measured in meters. The first part of this question is asking, what's the velocity after 3 seconds? So the velocity function can be found by taking the derivative of the position function. So we have, if this is my original, I have s of t is equal to 2t cubed minus 21t squared plus 60t. I'm going to take the derivative of that. I'm going to bring my power down. So my velocity function is going to be equal to 3 times 2 is 6t squared. Then I have negative 21 times 2, which is negative 42t, and my 60t just becomes 60. So that's my equation, but this is asking me what the velocity is after 3 seconds. So what I need to do here is I need to say, well, when time equals 3, what is my velocity? So I'm going to say my velocity when time equals 3 is equal to 6 times 3 squared minus 42 times 3 plus 60. So when time equals 3, my velocity is going to be negative 12 meters per second. Don't worry too much about the negative. That's just indicating the direction. Okay, the next part of this asks, when is the particle at rest? Well, the particle is at rest when my velocity is equal to 0. So I'm going to set my equation, my velocity equation, equal to 0. And that's 6t squared minus 42t plus 60. And really, this is just asking me to find my zeros for this equation. So I'm going to pull out a greatest common factor out of there. And that will be 6. So I can pull 6 out of everything. I'm left with t squared minus 7t plus 10. Now I need to factor this to find my zeros. So when I factor this, I get t minus 2 and t minus 5. So I'm going to have two spots where the particle is at rest. So the particle is at rest the particle is at rest when time is equal to 2 seconds and when time is equal to 5 seconds. So the last part of this is asking, when is the particle moving in a positive direction? And that's going to be when it's above the x-axis. When it's above the x-axis. So my velocity, where is my velocity greater than 0? So now what we want to know is, when will 6 times t minus 2 times t minus 5 be greater than 0? So if we just put this quickly onto the graph, I know that I have a 0 at 2. I know I have a 0 at 2. I have a 0 at 5. It's going to turn around somewhere underneath of there. I'm not too worried about the vertex at this point. And so really what I want to know is, I want to know, well, where is it? Where is this going to be above 0? Where is the velocity above 0? And the answer is, well, it's above 0 when it is less than or equal to 2. So at time greater than or equal to 0 or less than or equal to 2, and then it's also above 0 when t is greater than 5. Let's look at one more example, and this is going to be the last example for this particular unit. I said it was a short, for this particular lesson, I said it was a short one. So, the distance above the ground of a ball thrown directly upward in meters after t seconds is represented by d equals 25t minus 5t squared. So the first part of this question is just asking us to determine the velocity and acceleration. And what this is really asking you to do is to find the functions for velocity and the function that represents the acceleration. And to do that, we're going to use the derivatives. So what do I know about finding velocity? Well, I know that my velocity derivative is going to be, or my velocity function is going to be the derivative of my position function. I know my position function, so I'm away to the races. So I just need to know the derivative of 25t minus 5t squared. So my velocity function is going to be equal to, so the derivative of 25t is just 25. Derivative of 5t squared, I'm going to bring the 2 down, multiply it by the negative 5. That gives me negative 10 and t. Now we're going to do the same thing to find the acceleration. So remember, the acceleration function is going to be equal to the first, or the derivative of the velocity function, which is also the same as saying the second derivative of the position function. So now we're just going to take the derivative of this. So my derivative of 25 is 0. I don't need to include it. My derivative of negative 10t is just negative 10. So now I have my two equations. The next part of this question is asking, what is the initial velocity? And this is going to be the velocity when time equals 0. So what velocity did it start out with when the ball was thrown into the air? So we want to know the velocity when time is equal to 0. So I'm simply going to use my equation, my velocity equation, this one here. So I want to know the velocity when time is equal to 0. Well, that's 25 minus 10 times 0. So my initial velocity will be 25 meters per second. The next part of this, part C, is asking to determine the maximum height of the ball. So the ball will be at its maximum height when the velocity is equal to 0. This is the vertex of the parabola. That's where the slope is 0. So let's take a look at what this velocity time graph actually is going to look like. So let's just get this on here. So if I want, let's map this out a little bit. So I know that my equation for this is negative 5t squared plus 25t. I need to know some key pieces of information. I need to know my zeros, and I want to be able to figure out the vertex here, because that's really what question C is asking us, is what is going to be the value when we get to the vertex. So I'm going to pull a greatest common factor of 5t out of there. That leaves me with t minus 5. This is telling me that I have a 0 at 0, 0. So that's at 0, 0. And I have another 0 at 5 and 0. So let's put that on the graph. So I have one here, and then 1, 2, 3, 4, 5. I have another one here. Okay, now what else do I know? Well, I know that this is opening downward because my A value is negative. I'm not too worried at this point about exactly where that's going to be. But this is what this is going to look like. So from this graph, we can see that the ball is slowing down. This curve is slowing down. So as the ball is getting closer and closer and closer and closer to the top, it's going to reach its maximum height. And when it reaches that maximum height, for a split second at the very top, it's no longer moving upward, but it also hasn't started to fall back to Earth yet. And so this is the point that we're looking for, where the velocity is now equal to 0. So to determine that, really, we want to determine the maximum height of the ball. So this is the vertex. What we're trying to find here is the vertex, or when my velocity is equal to 0. So I want to know my velocity is equal to 0. So I'm going to set my equation equal to 0. So 0 equals 25 minus 10t. 10t is equal to 25. So t is equal to 2.5. So this is telling me that my y value at my vertex is at time 2.5. So now let's put that back into our position time equation, or our position time equation, and solve for what the y value will be when time is 2.5. So we have 25 times 2.5 minus 5 times 2.5 squared. Sorry, my dog is barking. So when we work all that through, the height is at 31.25. So this tells me that my vertex will be at 2.5 and 31.25, which means that it will be at its maximum height. So max height when time is equal to 2.5 seconds, and that height will actually be, or its position will actually be 31.25 meters above the ground. And finally, this is asking us, what is the velocity when it hits the ground? So now we've talked about what's happening as it comes up to the top. Now we want to know what's happening right here. So we know that it hits the ground when t equals 5. So it hits the ground when time is equal to 5 seconds. So we're going to sub 5 into the velocity function. So velocity at 5 seconds is equal to negative 10 times 5. I know I flipped this around a little, but that's okay. It doesn't matter. Plus 25. That equals negative 50 plus 25. So my velocity when it hits the ground is going to be negative 25 meters per second. And all that negative means is that it's going down. So when it hits the ground, it's traveling downward. Upward in this scenario would be positive. So here are the homework questions. Give them a try. There's also a Desmos activity posted, and there's an exit ticket for today's lesson. As always, if you have any questions, feel free to give me an email.